Alice, Bob, and Eve explain pure and mixed states.
I've arranged all my books by author now. Each book is exactly where it should be. No ambiguity.
That's quite satisfying. Your neatly organized bookshelf reminds me of something in quantum computing. A pure state.
Oh, pure states? That's actually a perfect analogy.
How does my organized bookshelf relate to quantum computing?
In quantum mechanics, a pure state means we have complete information about a quantum system. The system is in a definite state, like how each of your books has a definite position on your shelf. Classical objects like this book are always in pure states. It's either in my hand or on the shelf. There's no ambiguity about its position.
But I thought quantum objects could be in superpositions?
They absolutely can. A pure quantum state can still be a superposition. The key is that we know exactly what that superposition is.
Think of this spinning top. If I know exactly its position, speed, and axis of rotation, it's in a pure state, even though it's moving in a complex way.
Similarly, a qubit in the pure state ket plus is in an equal superposition of ket 0 and ket 1. We don't know which value we'll get when we measure it, but we know precisely that it's a 50-50 chance.
So what would be the opposite of a pure state?
That would be a mixed state, where we have incomplete information about the system. It's like having a shelf where you're not sure which books are where.
Imagine I blindfolded you and rearranged some books. Now there's genuine uncertainty about the state of your bookshelf.
I see. So in a mixed state, the uncertainty comes from our lack of knowledge, not from quantum superposition itself?
Exactly. A mixed state represents a classical probability distribution over possible pure states. It's like saying the system is in pure state A with 30% probability and pure state B with 70% probability.
Pure states can be represented by single vectors in Hilbert space, like pointing to a specific book on your shelf.
And they always stay pure under unitary evolution, the fundamental type of quantum operations. It's only when we interact with the environment that pure states can become mixed.
So keeping a quantum system in a pure state is like maintaining a perfectly organized bookshelf in a room where no one else is allowed to touch the books?
Yes, that's why quantum computers need such extreme isolation, to prevent environmental interactions that would turn pure states into mixed states.
And pure states are essential for quantum computing because they allow us to harness quantum interference, the key to quantum speedups.
I never thought my organized bookshelf was secretly teaching me about quantum information theory.